Hello everybody, welcome to another video on calculus from Thomas's Calculus. This time we are going to do chapter 4, applications of derivative, specifically optimization. Let's look at a question. The question reads, an open top box is to be made by cutting small congruent squares from the corners of a 12-inch by 12-inch sheet of tin and bending up the sides. How large should the squares cut from the corners be to make the box hold as much as possible? So what they mean is to take a sheet of this nature and a 12-inch by 12-inch sheet and cut off edges of x by x squared. So if you cut off these four, you can fold it up. So I'll show you another picture. So you can fold it up to make a box. So if you cut large x's, like for example, if this is your 12-inch by 12-inch, if you cut large x's from the corners, large squares from the corners, you will have a small base but very high boxes, tall box with a small base. But if you cut a small x, then you will have a wide base and a small height. So what they want to know is the best x. This is the x, this area that's cut, x squared, that will give you the maximum volume. So let's look at if this is x, so this part is 12 minus 2x, and this is again 12 minus 2x. So if this area, let's take the area of the base, let's delete these and let's take the area would be equal to 12 minus 2x times 12 minus 2x. That's the area of the base I mentioned here. And the volume would be area times x. So area times x is the height of this box when you fold that x area. So it would be x times, if you multiply this by this, you'll get 144 minus 48. So that is 12 times 2 is 48, x squared plus 4x squared. This should actually be 40, I think I said 48x and I wrote 48x squared. And so the 40x squared you get by multiplying 12x by 2 is 24, 12x by 2 is 24, and you get 48x plus 4x squared. So the volume would be equal to, we multiply all this by x, so we get 4x cubed minus 48x squared plus 144x. So this is the volume of the box. So if you cut off a small section of x and you fold it up, you get a volume, and the volume will depend on x. So x is a variable of the volume. But if we plot the volume versus x, we check where the volume is x, where the volume is maximum. That would be the x that will make the volume maximum. So you can plot it. For example, I can show you a plot of that. So we see, I've shown the plot here. So we see as x is equal to 2, the volume of this function v equals x 12 minus 2x squared is maximum at x equals 2. That's, you can see it from a graph. But without a graph, let's see whether we can do this numerically. For example, if we the derivative of v with respect to x, dv over dx, and make it equal to 0, we see the gradient at the maximum is 0. See, the gradient at the maximum is 0. If you draw a tangent line, it will be 0. So, and make it equal to 0, we can get the x. So, let's do that. So, when you get dv over dx, let's see what happens. It is 4 times 3 is 12 x squared minus 48 times 2 is 96x. You reduce the power by 1. You're using the power rule here, plus 144. So we have 12x squared minus 96x plus 144. So we take the 12 as a common factor. So we have x squared minus 8x, because 12 times 8 is 96, plus 12. Now let's factorize this again. So we know that we can write 12 as 6 times 2, and 6 times 2, if it's minus and minus, minus 6 times minus 2 is minus 8. So we can write it as, I'll change the color, 12 times x minus 6 x minus 2. That is the when you factorize this, that's what you get. So this becomes 0 when x is equal to 2 and x is equal to let me write and instead of that sign, and x is equal to 6. Now out of these two values, we need to select the correct, because there's only one value that makes this maximum. So let me show you how to choose that. So let me quickly write what we did in the previous slide. V is equal to x 12 minus 2x squared dv over dx is equal to 0 at x equal to 2 and x equals 6. Let's assume that we do not know this. We do not know, we have not plotted the graph, so we do not know where this value maximizes. So if we take x equals 2, we see that the area from this picture, area is equal to 12 minus, if x is equal to 2, 12 minus 4 times 12 minus 4. So we have 8 times 8, but as x is equal to 2. But x is equal to 6, we have area equals 12 minus 2x is 6, 12. 12 minus 2x is 12, and 12 minus 12. So area is equal to 0. So that's the minimum. And this is when the area is maximum. So we see when x is equal to 2, the area of this is maximum, or in other words, the volume is maximum. Here area is 0, so volume is equal to 0 here. When x is equal to 6, that's when the volume is equal to 0. When x is equal to 2, we see the volume is equal to maximum. So the answer is x equal to 2. Let's do one more question. Next question. You have been asked to design a 1 liter can shaped like a right circular cylinder. What dimensions will use the least material? So we need minimum material here. So let's look at the 1 liter can. So if we look at a volume of a cylinder, volume of the cylinder would be the area of the base times the height, right? So area of a base is 2 because this is r, right? 2 it would be pi r squared, it's not 2, sorry, it's pi r squared. That's the base, times height is pi r squared h. Now pi r squared h, we are told that is equal to 1 liter, which is equal to 1000 centimeters squared. So we'll write this again. So pi r squared h is equal to 1000. We'll leave the units as r is centimeters as well. So this is first equation. Then the second equation is the area of the tin. Area of the tin and area of the can made out of tin. So the area would be the base plus the base, because it's not an open can, so there's 2 bases, plus the sides. So the area of the base would be pi r squared. Area of the top, this is the top, and this is the bottom, is pi r squared. That's area of a circle, and this is the circumference. So if we take this and cut it open, we cut from here and open, this circumference would be the round of the circumference of this circle would be 2 pi r. That's the circumference. And if you, so the circumference here would be 2 pi r and the height would be h. So that's the area. So let's write the area as 2 pi r squared, that's top and bottom, plus 2 pi r times h. So this is the equation number 2. So what they want is minimum A min. They want the minimum area. So if we, but when you look at the area, we see there are 2 variables, r and h. So to minimize the area, it's best that we have 1 variable. So we need to replace h or r by this equation of 1. So since r appears twice and h appears only once, let's take h from here. So we'll take h from 1, we say, write 1 again, h pi r squared h is equal to 1000, and that makes h equal to 1000 over pi r squared. And we substitute to A. So A minimum would be 2 pi r squared plus 2 pi r, h is 1000 over pi r squared. So we'll cross off the common terms. So we have, sorry, I meant to cross it off with blue, and then we have r there. And after we cross off, we have 2 pi r squared plus 2000 over r. So now we want to minimize a, right? So what do we do here? If we look at the function, a equals, that's what we got in the previous slide, 2 pi r squared plus 2000 over r. And if we plot it, we see that at this value of r, there is a minimum. It's a little complicated. The r is a little complicated. It's cube root of 500 over pi, but you get a minimum. So at this minimum, at r, you can get the minimum area for 1 liter can, minimum area of tin for 1 meter can. So let's 1 liter or 1000 cubic centimeter can. So let's do this. We'll differentiate a with respect to r. We have 4 pi r plus, now this if you take this only, let me write this in another color. So if you take 2000 r to the minus 1, then we'll get, if you use the power rule, we get minus 2000 d over dr is equal to minus 2000 r minus 2. So let's write it here. So then it's not plus, it is a minus, and we have minus 2000 over r squared. So we have to make this equal to 0. So when you make this equal to 0, we have, let me write that again, 4 pi r minus 2000 over r squared equals 0. And we take this term, we take this entire term to the other side. So then we get 2000 over r squared equals 4 pi r, and then we take r to the other side, we cross multiply r to this side, then we get, and we take r, and then we take 4 pi down, then we get r to the power 3 by taking r to this side is equal to 2000 over 4 pi. So if you want me to do this separately, so we can write it as 4 pi, I'm going to bring r to this side, so r to the power cube is equal to 2000. Then we say r to the power cube is equal to 2000 over 4 pi. So we can cross off, there are 4 500s in 2000. So r is equal to 500 over pi cube root of 500 over pi. Now that we have found r, we know h is equal to 1000 over pi r squared. So we can substitute r here. So for example, let me write this as r as, when it should be about 5.42 centimeters, and accordingly when you substitute r squared here, h would be 1000 over pi 5.42 squared would be a value of 10.84 centimeters. So that's the answer. So the next question is, a rectangle is to be inscribed in a semicircle of radius 2. What is the largest area the rectangle can have, and what are its dimensions? So the question is, there is a rectangle inside a semicircle. So this is the picture. So we have the rectangle inside a semicircle. So we say the radius is 2, and we have this side as x and this side as x. So we have area. If this is h, area would be is equal to 2x times h. This is an x times h. I don't like to use a cross here. Let's use a dot here, times h. And h we can, since this is a rectangle, we know from Pythagoras' theorem, we know x squared plus h squared is equal to 2 squared. So h is equal to 2 squared minus x squared, square root of that. So let me substitute this here from here. So we put this here. So a is equal to 2x times square root of 4 minus x squared. So let's rewrite this. 2x times 4 minus x squared to the power half. So this is the area. To get the largest area, what we need to do is we have to maximize the area, find the x that maximizes the area. So the way we do that is, it's a single variable function, so we don't have to do anything other than differentiating it. So dA over dx, we have to find the dA derivative and make it equal to 0. So this looks like a function. It looks like it's two functions. This is one function and this is the other function. So when it's two functions, we have to derive one function to get the derivative of one function, multiply by the other, and add the derivative of the other function multiplied by the first function. So if this is sorry, I should change the color of, if this is f1, and this is f2, derivative would be f1 times f2 derivative plus f2 times f1 derivative of f1. So let me do this again. So derivative of the function f1, we first write the function f1 as it is. So we say 2x, and then we get the derivative of f2. Derivative of f2 is, because there is a half, we use a power rule, so we say half times 4 minus x squared. Then we subtract 1 from the half, we get minus half, and multiplied by the derivative of the function 4 minus x squared, that is minus 2x. And that is the first, that is this part of the equation, and we add to the function f2, we'll just write the function f2, 4 minus x squared to the power half, and get the derivative of 2x, which is 2 alone. So if we take the first part of the equation, I'll draw it in this. If we take the orange part of the equation, we can write it as, we can cancel these out, and we bring this 2 minus 2x to the front. We have minus 2x squared, and we bring this part below to the denominator. So we get it as 4 minus x squared to the power half, and then we add this part. I'll draw that in a different color. We add this part of the equation, which is 4 minus x squared to the power half, and we get 2 to the front here. Okay, so let me rewrite the area with dA over dx. We found it to be minus 2x squared over square root of 4 minus x squared and plus 2 square root of 4 minus x squared. This is equal to 0. So what we'll do is to minimize this, we have to make this equal to 0. So they want the largest value, so to maximize this, so we have to do a max. So to make this equal to 0, let's take this to the other side, or let's multiply both sides by square root of, we'll multiply the entire equation. Let's call this equation 3. We'll multiply equation 3 by square root of 4 minus x squared. So when you multiply the entire equation by that, we get minus 2x squared plus 2 times 4 minus x squared, because when you multiply this by this value, you get rid of the square root, is equal to 0. Now what we do is we'll just multiply this value. So we'll take minus 2x squared plus we have 8 minus 2x squared. So this is 4x squared, and we equal to 0. We can take this 4x squared to the other side. We have 4x squared equals 8. So we have x squared equals 2. So x is equal to plus or minus square root of 2. So that's the answer. When x is equal to, when the radius of the semicircle is equal to plus or minus 2, that's when you get the, let's look at the question again. What is the largest area? So that's the largest area you get of an inscribed square within a circle when x is equal to square root of 2. Square root of 2. That's when you get the area of the where the area of the square would be largest. We'll do one more example. Next we'll do a question from Thomas's Calculus, exercise 4.6, question number 9, designing a tank. Your ironworks was contracted to design and build a 500 cubic feet square base open top rectangular steel holding tank for a paper company. So the tank is to be made by welding thin stainless steel plates together along their edges. As the production engineer, your job is to find dimensions for the base and height that will make the tank weigh as little as possible. In other words, we need to find the area of minimum area, so that minimum area of the tank with steel plates, so that it will weigh as little as possible. So let me draw the tank. Let's say we have a tank with a base of, let's say all A's, and then the height of the tank is, let's say it's h. So we have a tank of this nature, and it's made out of thin plates of steel. So if we say V is the volume is equal to this plate A squared, area of that plate, plus H. That's the volume. And we are given the volume to be 500 cubic feet. Okay, we'll keep the cubic feet as it is. We'll write it down. Feet to the power 3. That's the volume. And the area, surface area, we'll call it SA. Surface area would be 1A squared, that's the base, A squared plus AH is one plate on one side plus AH, the plate on the other side. So this would be this, that's what I'm talking about, AH plus AH plus AH, because there are 4 plates here. So that SA would be equal to, surface area would be equal to A squared plus 4AH. Now we have to reduce the surface area so that the tank will weigh as little as possible. So so the way we do it is, we know we'd have to take the derivative with respect to which, A or H. So because there are 2 variables, we want to get rid of one variable. So let's try to get rid of H from V. So we know V is equal to A squared, H equals 500. So H is equal to 500 over A. So if we substitute this to the surface area, that's 2, we'll have 2, from 2 we'll get SA equals A squared plus 4, let's do second is here, not this, because I've simplified it further. So we have 4A instead of H we put, sorry, this should be A squared, 4 instead of H we say 500 over A squared. So we can simplify this further as A squared plus 2000, because 500 times 4 is 2000, and we can get rid of one of these A's because we can simplify that. So we have A. So that's SA. Now next thing we need to do is I can rewrite this as A squared plus 2000 over A. So next thing we need to do is, now we have the area with a single variable A, we can differentiate it with respect to A, and then we'll make that equal to 0 to get the minimum surface area. Let me rewrite this. SA is equal to A squared plus 2000 over B, which is, sorry, A, that's the surface length of the bottom of the tank, that is A, and let's get DSA, surface area over A, and if we differentiate this we get 2A plus this is, let me differentiate this on the side, 2000 A to the power minus 1. We multiply by this, a power rule, A is the variable, it's minus 2000 A to the power minus 2. So this is minus 2000 over A squared. We make that equal to 0. So when we do that, we take the 2000, let me write it in a different, we take this term to the other side and that makes it positive. So we have 2A equals 2000 over A squared. Now we cross multiply, so we get 2 A to the power cubed is equal to 2000, and we divide both sides by 2 2, then we get a to the power 3 is equal to 1000, and 1000 can be written as 10 to the power 3, a to the power 3. So a is equal to 10 feet when the derivative of SA is equal to 0. So this is the minimum where A to give a tank that weighs the least. So if you make an A of this nature, a tank with a base of A, we have to find the H, of course. You will get a tank when A is equal to 10. You'll get the minimum surface area, making it very lightweight. So H is equal to, let me go and check what H is. H is equal to 500 over H square, A squared. H is equal to 500 over A squared. So H is equal to 500. A is 10, A squared is 100, so H is equal to feet. Okay, so that's the answer of this question. So when A is equal to 10 and H is equal to 5, you can make a box that will weigh the least, but it can hold a volume of 500 cubic feet. Next, we'll do the 11th question. Designing a poster. You are designing a rectangular poster to contain 50 square inches of printing within a 4-inch margin at the with a 4-inch margin at the top and the bottom, and 2-inch margin at each sides. What overall dimensions will minimize the amount of paper used? So let's look and let's draw a picture. So we have, let's say we have a poster like this, and they want to print only inside, and this would be a 4 on the bottom, 4-inch at the top, and they want to keep a 2-inch margin on the left side and 2-inch margin at the right side. So if we take the width of the printable area, that's the printable area, let me use a different color, as printable area as W and printable area width as W, height as H, then this area would be W plus 4, and this length would be H plus 8. Okay, so let's write the equations. So the printable area, the area of the poster, not printable area, area of the poster would be W plus H, W plus 4 times, sorry, I should write this better, W times 4 plus H plus 8. That's the area of the poster. And the printing area is W times H is equal to 50 inches squared. So let's substitute for H here. So if you substitute for H, we get H equals 50 over W, and then we will take this H and substitute it here. So let me delete that to make it easier. So or let's use this color, we use it as H. So we have W plus 4 and H is 50 over W plus 8. Okay, so we know that we have to minimize this. We have to minimize A. So we have to minimize A. So the way to minimize A is we differentiate it and equal to 0 and make it equal to 0. Before we differentiate it, we'll multiply this and simplify this. So when you multiply this, we multiply this by this, we get 50, and we multiply W by 8, we get 8W. Then we multiply 40 by 4 by 50 you get over W, we get 200 over W plus 4 times 8 is 32. Now we can simplify it easily. So we do dA over dW, because we have only one variable, we can easily simplify this. When we simplify this, it's a constant that goes to 0, and I write it as 0 plus 8 plus, now this is equal to W over, we'll take this term only, and I'm going to differentiate this here. So this is 2 is equal to 200 over W is equal to 200 W minus 1. Then when you differentiate it, D over dW, you get minus 200, because you multiplied by the power, this is a power rule, W minus 2. So here we get, I'll write it here, it's some negative 200 over W squared, right? And then we have, when you differentiate a constant, you get a 0. So we have, and we make this equal to 0. So let's write this again, plus 8 minus 200 over W squared, and we make this equal to 0 because we want to get the minimum area. So minimum area, we make it equal to 0. So we take this to the other side, we take this part to this side, then we have 200 over W equals 8. Then we see that 8W equals 200 and W is equal to 50. So no, W is equal to, sorry, I made a mistake here. So this is W squared. So this should be W squared. So W is equal to not 50, really W is equal to 5 here, because W squared is equal to 25. We'll say W squared is equal to 25, W is equal to 5 inches. So if W is equal to 5, then we know H is equal to 50 over W is equal to 5, H is equal to 10 inches. So that if you use W equals 5 and H equals 10, you get the minimum amount of printed area. But if you want to get the minimum amount of paper used, we have to add, the W would be 5 plus 4 and H would be 10 plus 8. So the minimum paper area would be 5 plus 4 is 9, H plus 10, H is equal to 18. So that would be the answer here. So that's all the questions I'm going to solve. I would encourage you to go to 4.6 in Thomas's Calculus, exercise 4.6, and continue to work on problems of this nature. These are two of the recommended problems. I will problem number 33 and problem number 34. These are two recommended problems that you could do after watching this video, problem number 33 and problem number 34. And if you have any questions, please comment below this video. Thank you. See you soon.